kid's standing up there. That's 15 meters from the top of the building to the floor. The kid kicks the ball and kicks the ball with an initial angle of 0 degrees. Right, just kicks it horizontally. And I just want to figure out where it hits the ground. So use what we talked about the other day. I would strongly encourage you to organize your information the way I've got it set up on the board. So with a vertical and a horizontal, and write in the information that you've been given. And I'd also encourage you to remember to take a moment and make a decision about what you're going to call positive or negative. Okay? Let's take a few minutes. I think it's better at this point that you guys bat these around than I just show you what to do. Here. So your first job, I think, is to identify what's been given to the best of your ability. And remember that these problems separate out the horizontal from the vertical component of velocity. And you're then asked to work the problem separately, a vertical portion and a horizontal portion. But remember, we are observing the same event, and it's actually moving in 2 dimensions. So time is always the same for both of these. So you're always trying to figure out when something happened, because it's going to be the same for both. In this case, the ball falls 15 meters. That's the whole point. It falls 15 meters. And gravity is what brings it to the ground. But at the same time, it was launched with a speed of 5 meters per second and an angle of 0 degrees. Now, you can just convince yourself of what that means, or you can recognize that the sine of 0 is 0, and the cosine of 0 is 1. All right, 5 times 1. And then if you've decided that up is positive, then those two have to be negative. Well, that suggests you have enough information to do this problem. There are 3 pieces of given information. There is probably a motion relationship that could be used to figure out the time. So do so and work to your solution. Whatever you get for the time here is going to be equal to the time here. This is kind of the pedestrian version of this problem. There's more we're going to do here. So work through, and I'll pick on one of you in just a minute now that I've given you kind of a roadmap. All right, folks. This one wasn't too bad, was it? So if you worked it out, you realize you probably used negative 15 equals 1/2 times negative 10 t squared plus 0 times t. That look good to you guys? You recognize which one I've chosen? So you found that t is equal to square root of 3. So like 1.7 seconds. That look good? All right. And I told you where the ball struck the ground. All you had to do is take delta x equals 5 times 1.7. And where's that, like 8? 8.5? This is kind of the pedestrian problem, right? There's not much here, very procedural. Would you agree? I want to, go ahead.
Is it okay if I plug in the horizontal?
Now, you're going to need to be flexible with these questions, and remember kind of the stuff we did with motion equations from earlier, but also add to it what we did with vectors just a while ago. So let me ask another question. Do we understand that when we reach here, the object has both a vertical and horizontal velocity? Right. The vertical velocity has been growing the whole time because it's falling downwards, and it had 0 vertical velocity at launch, but gravity acted on it for 1.7 seconds, correct? At the same time, it was moving horizontally as it went from the top of the building to the bottom of the building. In fact, what is its horizontal velocity just before it strikes the ground? 5 meters per second. Does the horizontal velocity change as it moves through the air? It does not. There's no acceleration in the horizontal direction. So it just makes it to the ground at the same horizontal speed. what angle does it strike the ground? Take a minute, think it through. You should be able to do this. I'm not asking for anything new. I'm just asking you to put some things together that you've already done. On at least 2 papers, a bit of an issue. So before we go any further, this is Vy, right? It started with a Vy naught equal to 0. And as the ball has moved through the air, at various locations as it's moved, its vertical velocity has been increasing because gravity's been acting on it, correct? So it acts on the ball for 1.7 seconds over a displacement of 15 meters. Pick whatever you want, but figure out how fast it's going downwards when it hits the ground. I would probably use Vy squared minus Vy naught squared equals 2a delta y, only because at least it's using all given information. Right? This is stuff that we knew from the very start of the problem, so I'm not relying on anything that I solved for earlier. And figure out what Vy is. When you do, you're going to get negative 17.3 meters per second. Now, this part, and do we need to work that out for a second? You'll take the square root. Square root is plus or minus. Choose the negative one because it's downwards. Are we good to move on? I can. Vy squared minus 0 squared equals 2 times negative 10 times negative 15. Do you see it? You see why I chose those things? Okay. Do I have to do the arithmetic too? So 10 times 15 is 150, times 2 is 300. So Vy is plus or minus the root of 300, which is 17.3 negative. That makes this 17.3. Okay? Now, here's the thing. You've been adding vectors already. Our actual velocity vector is 5 meters per second in the x-hat direction minus 17.3 meters per second in the y-hat direction. That's our actual velocity vector. So as you're finding the angle, don't forget the way in which we were told to figure out the addition of vectors. Create the appropriate triangle. Understand the angle that you're actually finding. Remember, add them tip to tail, make a right triangle. Our resultant is here, which you could figure out by using the Pythagorean theorem if you wanted. I didn't ask for that. I asked just for the angle. And for the angle, tangent theta is 17.3 over 5, which is probably 70-something degrees. Now, you don't have north, south, east, or west for this one. So when you're going to state direction here, it's negative with the respect to the horizon. Right? This is being measured relative to the horizon. And normally for an angle like this, you'd be asked to figure out the angle relative to the horizon. So give it appropriate context, but make sure you indicate that it's negative with respect to the horizon. So this is actually an angle of declination instead of inclination. We need to see another one, but this is just our start. I'd say this is what I like to call a level 1 problem, because it's pretty easy. And it's easy because of this 0. That 0 makes it easier. In perfect soccer spirit, let's say when you're watching the footy, they kick the ball, and they kick it off the ground, like maybe the goalie's just kicking it downfield to get it away from his goal, and he kicks it at, we'll go with 25 meters per second at an angle of 15 degrees. How far downfield does the ball land? I like to call this a level 2 problem. It's got a few more things in it, but not really very much. There's something here that you have to figure out that you can use. So, not much more here, but I'll still say the best place for you guys to start this would be to break your problem up into vertical and horizontal. There we go. So it's not a trick, so as much as to say that you have to recognize that the problem shares similar things to what we talked about with the first portion of this unit in one dimension. If I throw a ball straight up and it comes back down to where it started, delta y is 0. So in this case, delta y is 0. It lands at the same height that it was kicked. Comes up, comes back down. But the initial y velocity is not 0. The initial y velocity is 25 sine 15. So it's clearly got a y component of its velocity. And Vx, 25 cosine 15. It clearly has a horizontal component of its velocity. So this is like 6.4 meters per second and 24 meters per second. I would keep decimal places there. Any question about these choices? Still 10 meters per second squared for gravity? What do you want? Do you want up to be positive or up to be negative? And I think to the right being positive makes perfect sense. So if that's true, this is positive, but this is negative. At this point, you've got 3 pieces. Still the same kind of problem. Figure out how long it's in the air for. You need this. That way you can use it over there. You've got 8 more minutes, and I think there's more that you need to see. I'm going to use a motion equation to figure out time. Probably the same one. So I'm going to use delta y equals 1/2 at squared plus vy naught times t. That's going to be 0 equals 1/2 times negative 10 t squared plus 6.4 times t. Now, technically, to do this correctly, I need to factor out a t. And I don't like to be complacent with stuff like this. There's a reason why you should do it this way, and get the fact that one of your t's is 0 and one of your t's is 6.4 divided by 5. There's 2 values for t here. We asked our math to tell us when the ball was on the ground, and it was on the ground twice. Once at the start of the problem, t equals 0, and once after it'd been in the air for just over a second. So once we know that, I get approximately 1.28 for my time. So that's 1.28 here, 1.28 there. Again, almost every one of these problems has you solving for the time on one part and using it on the other. So now delta x equals Vx times t. So delta x equals 24 times 1.28 to get you approximately 31 or 32 meters, depending on how you rounded. This is the pedestrian level part of the problem. Meaning the part of the problem that's just the plug and chug, exactly like we did before. I'm going to ask something else. I want to see if you can roll with the change. What's the maximum height attained by the projectile, and where does that occur? So I want to know what is the maximum height attained by the projectile, by the ball, and where does that occur? So you're looking for two things, but you may have to reset what's here. Now, I think one of these answers you could probably guess at. It probably makes it to the maximum height in the middle somewhere. But what that maximum height is, you probably have to work that one out. So let's start with, how would you adjust this to figure out the maximum height? Talk it out, and I'm going to ask some of you. All right, as there are only 2 minutes left, can somebody tell me one change I have to make to our information here to figure this out? Go ahead. I do believe this will be a different time. Yes. So, what other change? Like I do think I'm finding the time again, or at least I'm finding something different than I found before. Well, I will need range. It's where it is, that's true. Go ahead.
Where it is on like the X.
And where it is on the Y.
I know, yeah.
So that means I don't have delta Y. I'm looking for how high it goes. Go ahead.
The final velocity.
That's right. It reaches its maximum height when the final velocity is 0. So we're talking about a different trip altogether. We're talking about this trip, right? The trip that makes it just to this point. So we're not talking about the whole trip back to the ground, just to this point. And the maximum height is always achieved when the final velocity is 0. This is a new problem, one that involves different information. So now this is the information I'd use to figure out delta Y. Again, it will tell me how high the object makes it. It doesn't tell me where that happens. I'm guessing that it happens halfway. That's a guess. But I think it's a pretty good guess because I think it's symmetrical. But if I want to figure out the maximum height, I would just use the motion equations again. This is no different a problem than what we did way back at the beginning of this in middle August. So I would say 0 squared minus 6.4 squared equals 2 times negative 10 delta Y. This will tell you the maximum height. Now the bell rings in a minute, but you really need to try something tonight. Retry this problem for 75 degrees. Please do. You're going to see something important. So please retry this whole problem, but use 75 degrees.